Hello all and welcome back to this course on digital systems. Having looked at the design and implementation of various flip-flops, the D, JK, T flip-flops, in the remaining part of this course we are only going to focus on what we can do with these flops. How can we build sequential circuits to achieve a certain functionality, to achieve a certain finite state machine that we wanted, right? And we will get there in a step-by-step manner. Okay, so what we are going to do today is we are going to look at the idea of a register. Okay, a register is basically a bunch of flops, right? And specifically D flip-flop. Okay, so it is something like this. Okay, for example, I'll show you a 4-bit version here, but typically this can be extended to an n-bit version as well. So you have the clocks running like this. I will just say I'll just pull this out, and I'm assuming the clock is just running through like this. Okay, it's running in the background and making a contact to the triangle wherever necessary. So right, so I have D0 Q0, D1 Q1, D2 Q2, D3 and Q3, right? So essentially this collection of flops allows us to do certain operations with it, right? And we'll see what operations they are, and we'll try to figure out how to implement various functionalities as needed, right? So this is, by the way, what you will even hear of in a microprocessor course. You will hear that there is a register A, there is a register B. So what will happen is typically there is an ALU, right, like this. So you will have a register A, a register B, okay, RA and RB, and this will talk to the ALU and you will get an answer out like this, right? Each of these could be either some n bit in general. N is typically nowadays in these microprocessors, it can even be 64 bits, 128 bits and so on, but otherwise it usually would be 32 bits some time back, right? So typically when we represent this bunch of flops, right, we may not necessarily get into drawing all n of them. We will just say, if it is possible, right, to show it like that, we will call this as D, we will call this as Q, and then this basically means it's an n-bit number. So I could equivalently draw this register like this, okay? And even when we come to the timing diagrams, I'll show you what I alluded to this earlier, but we will not get into D0, D1, D2, D3 as such. We will just talk about the collection of bits D0 to Dn-1 in general, okay? So now what is it that we can do with this, right? This most straightforward thing that we can do with this kind of a shift register, right? And just to clarify, what I meant here was, I'm going to assume that my clock runs like this, right? And wherever needed, I'm going to drop a connection. Okay, this is what I mean. So only where there's a dot, there's a connection. If the clock crosses D3 to D1, it doesn't mean there's a connection there, okay? So essentially this is what I mean by this other picture where the clock was running underneath and I'm just making the contact to the clocks here, okay? This is just a less cumbersome way of drawing it, okay? So now what I can do is to simply connect each of these D0, D1, D2, D3 to some input data I1, I2 and I3, right? And what I want to effectively do is I want to load this data into my output on the clock, right? So if I look at my input bits, right, I, right, and I will represent it like this, I0 to 3, right? I want to represent it obviously with respect to a clock, okay? So I have this, no, the rising edge, sampling edge must always happen well before, right? So the change happens let me just draw it a little more clearly. Okay, so this is my um, I, input I, and it's going to settle to the new value, right? This is the sampling edge again, okay? And like I told you, this will go from state 1 to state 2, you know, all the way to state 3, right? Like I alluded earlier, state 1, state 2, state 3 are just different combinations of zeros and ones for the I0 to I3, right? It can be anything. State 1 can be any one of the 16 combinations, state 2 can be any of the 16 combinations, and so is the case for state 3 as well. Okay, I don't care what that means. And then I am looking at my output Q, right? So if I look at what happens to Q, I really do not know what happened before this clock period here, because I do not know what was sampled at that instant. So this one I will just leave. I will say it is an unknown state, right? And then I am going to now sample the state 2, right? And Q will switch, right? Assuming there are no delays, right? This is just a functional simulation. Then this will switch to state 2, right? And at the next clock edge, it will switch to state 3. In this case, state 2 of Q and state 2 of I are exactly the same, because it's the same data that is being pulsed and is being transmitted to the output Q as is. Okay, but in other cases, if there is a combinational block sitting before the flop, right, then the input and the Qs need not match, and however they could correspond to the same state, right? So for now I will not worry about that aspect too much. I'll highlight it when I come to that. For now you can assume that these two are exactly the same because of the nature of this parallel load that we are talking about. Okay, so now the issue with this kind of a parallel load is that it just loads the data on I1 and I0 to I3 every single cycle. Okay, it's just not there's no other functionality that this particular block is able to implement, and therefore we would like to modify this circuit to a parallel load with control. Okay, so the way I want this, the behavior I wish to have is, I have a signal called load. If load equal to 1, okay, then my output should be equal to I, right? And let me again highlight this, 3 down to 0 should be equal to, yeah, so this notation means Q0 equal to I0, Q1 equal to I1 and so on, right? Now else when load is not high, right, I basically want my Q to remain in no change state. Right, this is sort of the pseudo code that we are writing for this particular thing. So let us see how we can implement this property now. I have a, these D flip flops as usual like this. Okay, and again I am going to draw this clock thing in a less cumbersome way. Okay, the same clock is available to everything here. Okay, and what I now want to do is I want to modify this circuit to the input. Okay, so what I'm going to do is I'm going to add a combinational block here, which will control and get me this behavior, right? So this is Q0, Q1, Q2 and Q3, right? So I have I0 here, likewise I have I1, I2 and I3. Sorry, I2 and I3. Yeah, right. Okay, so let me get this notation right. Yeah, and we are trying to now give an external signal here called load. Okay, so the idea is now for us to figure out what should be this load signal, right, and the what should be the combinational block that takes the load signal and the input and the Q output, so that we can implement this desired behavior here. Okay, so clearly we need something to gate the data, right? If load is 1, then the input should go through, right, else the input did not go through. Okay, so just look at this. The moment you see an if else thing in your algorithmic thinking, the best way to implement that is to go ahead and implement it with a multiplexer, right? So therefore this combinational block can be implemented in the following way. I'm going to say load. Okay, if the load is 0, then I want my Q input to come here. If my load is 1, then I want the input I to come here, and that is what is going to go to my D of the flip flop. Okay, so this is 0, 1, right? And what is a multiplexer? Ultimately, the multiplexer is nothing but something like this. Okay, so you basically control the case of 0 with load bar, and this is load. This is a select line of the multiplexer, and therefore I am going to give this as Q, I am going to give this as I, and then this is D, right. So that is all the multiplexer implementation in terms of basic gates is, right. And therefore I can easily replace this circuit diagram with the following here. This is my flop. I will just put a multiplexer here, okay. D, Q, zero and 1, and this is my parallel input I, okay. Now remember, I am now talking of multi-bit inputs, and therefore this is all 4-bit, this is 4-bit, this is 4-bit, okay, which basically means that when I expand it, it will become like this. So the equivalent representation of that circuit is actually like this, right. With this combinational block here, with this combinational block here just being a multiplexer like this. Load I and Q, and this is going to the D, that's all, right. So this is a very compact representation for us. You get Q here, and all these are multi-bit inputs. And now it's also interesting for us to look at the timing diagram of such a circuit. This is the sampling edge, right, and this is the clock, by the way, here, right. Now as usual, my I, and I will write it as 3 down to 0, right, with I3 being the MSB, I0 being the LSB. That really doesn't matter for now, because we are not treating this as any arithmetic number at this point, okay. The I is going to change from state 1 to state 2 to state 3 and so on. Okay. Yeah. So what I'll do, again I'm going to call this a state, actually I'll call this state 0 from now onwards, because it's a 0th state, I don't care. State 1, 2, 3, okay. And what I'm going to do is, I'm going to draw a certain waveform for the load signal, okay. The load I'm going to keep high at this point, okay. Then I'll skip the load at this point and then again go high for the third case, okay. So this is the pattern for my load signal. I want to observe what is the output Q and figure out the pattern for Q, okay. So for Q, what will happen, your again it is going to be 3:0, right. Now this is the first sampling edge, second and the third, right. So what is this? We have Q being unknown at this stage, because we do not know what was sampled in the previous clock cycle, right. And then load is high, right? And therefore the input that you apply is going to appear at D0, D1, D2, D3, and when you clock it, that will just appear at the output Q, right? So therefore this will go low. This will go to state 1. Okay, and like I told you in the earlier case, these two are exactly the same because there is no combinational logic that is altering this. It is just sending I directly to the output on the clock edge, right? So you come, and of course since it's a D flip-flop, remember Q will simply remain at that value until the next sampling edge, right? That's the only time that something can change. So you come to the next sampling edge, load is 0 at this point, right? And therefore whatever the value of Q was, it will continue to remain like this. There is no change. Okay, this I will explicitly write in this clock cycle, this is still in state 1. Okay, and when you come here, you are coming at the third clock cycle, right? Remember, let me write that this is n equal to 1, n equal to 2, n equal to 3. At the third clock edge, what is happening is load is high again, and therefore that data will appear at the output like this. Okay, and therefore this is going to be 3, right? So whatever I've drawn here, the Q appears to have a small delay, but that's okay. Otherwise you have to make sure that the transition happens exactly at this edge like this. Okay, but I'm not going to worry about that for now, because in reality you will have a small delay there, right? So effectively this is again exactly the same, right? And what has happened is this state has got ignored, right? And I'd like to repeat, state 1, state 2, state 3 could be any combination of zeros and ones of the input. Okay, any of the 16 combinations of I0 to I3 or I3 to I0 as the case may be, and I'm just talking about one input combination going to another input combination when I say state 1 to state 2 to state 3, right?